In the traditional software development model, compilers, assemblers, and linkers are used to create executable programs. To reverse engineer these programs, we utilize tools known as disassemblers and decompilers. Disassemblers reverse the assembly process, producing assembly language as output based on machine language input. On the other hand, the compilers aim to generate high-level language code such as C, Python, or Java when provided with assembly or machine language input. The concept of source code recovery is appealing in the competitive software market, which drives ongoing research in developing effective decompilers. However, the compilation presents several challenges. These are: the compilation process is loosey. When a program is compiled into machine language, variable and function names are lost, and the type of information must be inferred from data usage. For example, determining whether a sequence of 32 bits represents an integer, a floating point value, or a pointer requires careful investigation. Compilation is a many-to-many operation. The translation of a source code program to assembly language can occur in multiple ways, and the reverse translation from machine language to source code can also have various valid representations. Consequently, compiling a file and immediately decompiling it often results in significantly different source files compared to the original. The compilers are language and library dependent. Different programming languages and libraries have distinct conventions and features. Processing a binary produced by a Delphi compiler with a decompiler designed for generating C code can lead to unexpected and nonsensical results. Similarly, attempting to decompile a Windows binary with a knowledge of the Windows programming API may not produce useful output. Accurate assembly is crucial for precise decompilation. Errors or omissions during the disassembly phase can propagate and affect the quality of the compiled code. Disassembled code can be verified against processor reference manuals for correctness, but no definitive reference manuals exist to validate the output of a decompiler. The process of disassembly and decompilation is not only useful for reverse engineering, but it also has implications for network security. Understanding the inner workings of software, including vulnerabilities and potential exploits, is crucial for ensuring the security of your computer software. By analyzing disassembled code, security professionals can identify potential weaknesses or malicious behavior in software. This knowledge helps in developing effective countermeasures such as intrusion detection systems, firewalls, and antivirus software to protect networks from attacks. Furthermore, the compilation can assist in the identification and analysis of a malware. Reverse engineering malicious software provides insights into its functionality, communication methods, and potential impact on the computer systems. This information enables security teams to develop effective strategies for detection, containment, and removal of malware from compromised systems. Overall, disassembly and decompilation play significant roles in both understanding software and enhancing network security. They empower security professionals to analyze and protect against potential threats, contributing to a safer digital environment.